Okay, so what we have seen so far is because the curl of E is 0, again, this is electrostatics, we get that E can be written as the gradient of a scalar. We call this the electric potential. And there are many ways to get the electric potential. One way is to find the electric potential due to a single charge and then add it up. And when you do that, what do you get? I wrote an expression as the integral. You do it for one single charge at a time, but we got something like what? Integral dq, but let me write this as d tau over the displacement vector. And if you look at Helmholtz theorem, this is exactly the expression from there as well, where the divergence of the electric field has been replaced by rho over epsilon naught. So this is one formula. If this integral converges, if this can be integrated. This is not always the case that this can be integrated. And I have mentioned that in my Helmholtz video, but I'll actually show you an example where this formula will not work. It is very simple. It will not work if the charges are not, it doesn't have to work if charges are not confined to a bounded region of space. But if charges are indeed not confined, it'll still work provided the charges decay as 1 over r cubed. Yeah? It's a rather steep requirement. Only then the R integral can be done. We'll find a violation to where this formula will not work. But when this doesn't work, there are other clever ways you can get an expression for V. Because all we need to do is make sure this is satisfied. So we have two, this is the requirement. This is a recipe. When this recipe fails, there may be other techniques, as we shall see today. So to have a clean argument, I'm going to slightly depart and talk about boundary conditions, and then we'll talk about the example that I want to show you. Okay? And I think I may have mentioned this before. When is physics interesting? At the bound, when things are not continuous. Yeah? Otherwise, it's fairly simple. The difficulty is just calculating things. But interesting physics happens where there's discontinuity. So imagine, if you will, you have a sheet of charge. And it has some charge density, sigma on it. And I'll draw this in two perspectives. The other one would be just at least locally at any given point. So this is this point. It can be thought of as a plane. Okay. This region, I'm just going to call this above, below. Well, which one is above? Which one is below? That's arbitrary. But I'm going to consider this as my normal vector, unit normal vector, and that explains above. The normal, unit normal points above. So what we want to do is look at the electric field over here and look at the electric field over here. And then let the value of the electric field approach the surface from above and approach the surface from below. And we'll see if they are in fact the same. We'll find out that they are not when there's a charged surface. So first thing we'll do is the simpler one. We'll try to compute the tangential component of the electric field. Meaning tangent to the surface. So what we will do is pick a loop and use Stokes' theorem and integrate. When I integrate, what do I get in Stokes' theorem? Well, del cross E dot dA of this area, meaning with the normal pointing this way, but that is 0, and which means, sorry, area is just area. The closed boundary, E dot dl, must be 0. So I'm going to call this H because it won't matter too much. What I'm going to do is let H go to 0 because we want to know what happens to the electric field. Okay, so I don't know which way the electric field is pointing. The electric field over here could point in this direction. But Stokes' theorem won't see it. This particular loop won't see it. What Stokes' theorem is going to see is only the component of A in the dl direction. So it is only going to see this part. Yeah? So this is going to be, what I'll do is this vector, I will denote this as E parallel above. The component of the electric field along dl. And why did I call it parallel? It is the component of the electric field. It is a component of the electric field that is parallel to the surface. There could be another one in that direction. That's no problem. I can do another loop in that direction. And the same thing applies over here. Yeah? And I'm going to pick a length that is not too big. Small amount. I know I've exaggerated here. That's for clarity, right? I'm going to pick a very small amount of length. I'm going to do a further assumption that the electric field does not change in the small amount of length. Yeah? If you want, you can take it to be the maximum value or something like that. There are clever mathematical ways to estimate it, but it really won't affect our argument. In fact, it won't. I'll show you why it won't. So then I would get, let me do this integral first. E parallel above, and I'm going to call it just dl, meaning this distance is dl. Then I'm going to skip the side terms for the moment. Then I'm going to go this way. The only problem with this dl and this dl is it points in the opposite direction. Not just yet. So maybe what I should do is I should do above, and then plus E parallel below dl, and I can't write anymore because it won't be recorded, I think. But what I mean by here is this is below. Okay? Maybe I can even avoid that confusion by doing below. Plus these two terms. It won't affect our calculation at all, so I'm just going to write side terms for the moment. It doesn't really enter. Why complicate it? Why even bother to write it down? What I want to do is take the limit as these two loops coincides with the surface. How do I do that? I simply let H go to 0. First of all, this is 0, by the way. Yeah? And then I get E parallel above. I'm going to write it and then explain it, huh? First of all, well, copy this down. There are a couple of missing things, and there's a sign that I need to explain. It should be intuitively clear to you, but let me go ahead and explain it anyway. Why did the side term go to 0? As long as electric field is bounded over here, if you're integrating over 0 length, it's going to be 0. Yeah? Let's make it a big number. Electric field equals, in that direction, equals 1,000 newtons per coulomb. So then you do 1,000 times the length. Let's say it's constant. Well, let the length go to 0. 1,000 times 0, 0. I don't care about the side terms. No need to bring this up. The second thing is also something we just mentioned. As you get closer, as the limit approaches, this DL is going this way, and this one is going the other way. So one is positive, or one is negative with respect to the other. That's all I care about. Okay? This is true for any such loop. If the integral of a quantity vanishes, that does not mean the integrand vanishes. But we've talked about this story many times over. This is true for any 2 points that you pick. Any 2 points within the short region. When is that true? When the integral of something vanishes over any domain. The only way that can happen is the integrand vanishes. So this implies I'll write this vectorially, and all this will disappear very soon. It sort of violates what I just said. It doesn't violate. Well, because there are other components. What did I begin with? Very good. It'll be discontinuous. Well, so parallel components are continuous. So what must be discontinuous? The normal component, correct. Yeah. Yeah? You sure?
I'm gonna have to see this.
See what?
Now I'm confused.
What are you confused about? Confusion is good.
I just said the normal is.
Well, I have to show that to you.
Yeah.
It's only half the story.
Yeah, that's what I meant.
Yeah. The parallel components are continuous. So this component is continuous. Now there is a matter of the other component. If one is the Stokes theorem, the other one is going to be divergence theorem. Yeah. Okay. Good. For Stokes theorem, you need an area and its boundary. For a divergence theorem, you need a volume and its two-dimensional boundary. Okay. Now let's worry about, and I think we did this before, it is exactly like the infinite conducting plane. You draw a pillbox. And this area, I'm guarding my chalk like no one's business, I don't know why. But so if this is the charged surface, the pillbox is half above and half below. It doesn't have to be equal measures of things. So here is the charged portion. So let me draw an easier picture as well. It looks exactly the same, except this is to be thought of as a cuboid, right? A volume with areas on both sides. And I'm going to use the divergence theorem. divergence of E d tau equals, what is it? E dot dA. This guy is rho over epsilon naught. Okay, and Ashik, to partially convince you, when we started out with the Stokes theorem, the left hand started out with being 0, hence continuous. Here the left hand side is not 0. Already you can see there's a problem. Okay, well, I'm going to write it for the moment as E dot dA, and then I'm going to worry about all the 6 sides in one shot. What are the two I'm going to let H go to 0. So I know this is a face, it has another dimension, but I don't care. I'm just going to call this H, and I'm going to let H go to 0. How many areas will have a non-zero contribution if I'm going to eventually let the H go to 0? Only the top and bottom. So I'm going to write 2 area integrals, and then I'm going to write plus stuff. Are we good?
In fact,
Yeah.
if you look at the normal directions of those sides of the box, which direction is this point?
Tangential direction.
Tangential direction, and you just showed that the tangential direction was
Yep.
right?
So what I'm going to do is call this one normal and maybe above. Below. And as I let H go to 0, N above is going to be equal to negative of N below 2. Once again, one will be a plus contribution, the other will be a negative contribution. So I'm going to do this integral. This pillbox is a small enough pillbox. Well, in the left-hand side, it doesn't matter. The charge contained in this cube is simply sigma times A. Surface charge. Frankly speaking, it doesn't even have to be a constant, because I do it differently than Griffiths. Once again, I'll show a certain integral vanishes for any area we pick below a certain area. And this is going to be E dot normal above dA plus E dot N below dA. And I'm going to collect all the terms because these are all, I don't know why I used uppercase. To be consistent with Griffiths. I'm going to write that integral. Oh, plus what? Yeah, don't forget the very important stuff.
Very important stuff that we don't care about.
Right.
You replace rho d tau because rho d tau is total charge.
Correct.
Right in terms of.
Correct. Rho d tau is the total charge contained in the pillbox. And for us, there's only charge on the surface, so good point. Rho d tau has been replaced by sigma dA. Yeah. So, should we, I'm not tall enough, limit, H goes to 0. I'm going to collect sigma over epsilon naught. Or let me bring that to the other side, just traditionally how it's written. E perpendicular, that's the language, that's the notation, above. What does E perpendicular above mean? Well, I'll tell you exactly what it means. Let's just understand it intuitively. Again, let me write the equation down below. Minus sigma over epsilon naught dA equals 0. Several things has happened in this step, so I want to clarify. First of all, what happened to stuff? Always get rid of your stuff. Yeah? All right. So my notation, E above dot N above is simply that. It's a short way of writing the component of the electric field as you take the limit from above. And same thing happens to below. Oh, yeah. The perpendicular component. The other one was the parallel component. This one is the perpendicular component. Remember, for parallel component, I just showed you one loop. Really, you need two loops. One for, it's a surface. You have two perpendicular directions of components. But if you do it once, you've done it many times. This is true for any area inside a small area. Actually, it's not even true, but that requires a little differential geometry. But it's true for any area. So the integral is 0 for any area that is chosen, like as we have shown this before, rigorously very early on. The only way that can happen is if the integrand vanishes, and then we get the discontinuity that Ashik was not quite convinced will happen, but it does, right? So the normal component of the electric field is not continuous, but the tangential component is continuous. Kind of neat, huh? And discontinuity is very suggestive of matter. This is true in many theories, under many circumstances. Yeah, there's a field has been replaced by some sort of a matter content. So it's a telltale sign. It's where interesting physics happens. We'll put this to practice very soon in the example that we're going to do. In fact, the next statement that I'm going to make, not so much the electric field, but how it relates to with respect to the potential. Questions? I'm going to combine the tangential property and the perpendicular property and write it as one simple vector equation. E, the entire E above minus the entire E below is equal to, let me know if this works for you. What is it saying? There is discontinuity only in the normal direction. Well, how much discontinuity is it? Exactly this much. This vector does not have any tangential component, so the tangential components are continuous. Yeah? This is not difficult to see, but the point here is every day we're piling on ideas, and it just gets piled on and piled on and piled on, and you have to keep the story alive in your mind the whole time. So I did this for the electric field. I want to do it very quickly for the potential. It's very easy. Why is it easy? For a potential, I don't have to worry about direction. And just to tell you the story, the potential is going to be continuous, regardless. I expected a mathematical question. Electric field is not continuous. The potential is continuous, but the potential is the derivative gradient of the electric field is the gradient of the potential. What gives? There's a result in math that I want you to hearken back to. Differentiability implies continuity, but continuity does not imply differentiability. So here you'll have potential that is continuous, but it's not differential. A quick picture. How do you know continuity does not imply differentiability? Can you think of a function? I know you can. This is continuous, but not differentiable here. This is exactly sort of the thing that has to happen to the potential. But let me go ahead and do it. Is that how you spell continuity? If I scribble enough, you cannot tell. And this, if I'm going to potential. So what I'll do, I will take a line integral above and below. And so recall then I can write V above minus V below is equal to minus, well, that's how we defined this in the first place, the electric potential. And this is my dl. Now what am I going to do? Let these 2 points come over here. In that case, yeah, that is equal to 0 as, for a better way to describe it, as above approaches below. Correct? Misusing the term. Nonetheless, when I say above approaches below, I mean you're not integrating over anything. As long as the electric field is bounded, we don't expect any infinities here. We get this to be 0 or V above equal to V below. Now remember, this all these statements has to be taken as V above, V below, truck. Yep. All these, the tangential component, normal component, all of that, when I say above, below, I really don't mean above, below. I mean when you take the limit as the above portion reaches the surface and the below portion reaches the surface. So the potential here must be continuous across a boundary.
Is this some way related to equal potential surface?
We'll get there.
Yeah.
It could be, yeah. So it's for a larger distance.
Yeah,
V at this point equals V at that point. You will see. Yeah, it is. That's when E equals 0 inside a conductor. We're there. We're almost there. So the electric field is not continuous, but the potential is. So I'll do an easy problem the easy way, but one has to be careful. And also I'll illustrate what I mentioned just now about the way to find the electric potential is not necessarily by doing a complicated integral. It is by carefully using other techniques when it's available. In this case, you could integrate it, but we'll do it in a way that we won't integrate it. And so what is the problem that I'm trying to do? There's a tougher integral version of this problem, but as you know, I'm kind enough to assign that as homework. So, simple problem. You have a solid sphere of radius r. And it has, we've done this before, it has a uniform charge, a charge Q that is uniformly distributed. Well, in fact, that means there's a charge density. What is it? So, well, there's a charge density rho, which is Q over 4/3 pi r cubed in the entire volume. We have seen that outside, the electric field is exactly given by what? Yeah, very good. KQ over R squared, R hat. The electric field inside is given how? We did this using Gauss's law. Yeah? I remember it was like harmonic, right? It was just proportional directly to R. So it was, we need the exact expression. We derived this in class, and I think I have written this down. It's KQ over R cubed. Let me make sure. And check your notes to verify this. Okay, so what's the problem? Find the electric potential everywhere. You could do it the tough way, integral of rho d tau over the separation distance. Okay, there's something to be learned about that. That is not so obvious when you do the inside part. But this is, using Gauss's law, we have this nice relationship. Here too, there's something to be learned about that. It's not very obvious. First of all, I'm going to, the technique I'm going to deploy is this guy. If you notice, for both inside and outside, the electric field is only radial and it has only R dependence. Yeah? So V is only going to be a function of R. Look at the formula for gradient in spherical coordinate system and find the R component.
Partial with respect to R.
It is just partial with respect to R. So this is, don't forget in our case, a negative dr V in the R hat direction. Oh, this is the answer what we've, yeah, it's uniformly distributed. There's no angular dependence, just spherical symmetry. Theta and phi won't show up in the, yeah. So let's find V out first, outside, which means I'll be using this expression. And I would get or rather, let me do it this way, dv dr equals minus kq over r squared, which implies what? Integral of 1 over r squared is minus 1 over r, thereby killing this negative. So I get kq over r plus some constant. When you integrate, there's always an integration constant. Now, what did we want? Whenever possible, when you have a bounded distribution, we want the potential to go to 0 as r approaches infinity. And that can happen, so v equals 0 as r approaches infinity implies c equals 0. And so we have that nothing miraculous about this. We have found this out before as well. Yeah? Fine. Let's just remember this fact and then do, not inside, but rather outside. I'm going to erase that, and I'm going to do the inside. So here I would get dv dr equals minus kq over r cubed times r. So now I get, I'm going to call it v in equals, what is it? Integral of r is minus, am I right? Minus, yep. Minus kq over 2r cubed. Is that true? R dr is r squared over 2 plus some constant. You're tempted to say, well, one thing, you cannot let r, you're not tempted to say that upon a little more scrutiny. You cannot let r go to infinity because it's inside the sphere to begin with. Yeah? So what do you do? If you want to know the potential inside the Death Star, you have to know what's on the surface of the Death Star. Continuity of potential. So I'm going to do this. That's what continuity means, right? And I'm not going to write this as constant. I'm just going to call it C. So then I have K cubed over 2R plus C equals K cubed over. Is that true? Please remember, if I make a mistake, it's on you, huh? So what does that mean? C equals KQ over 3R. Just bring that. No. What is 1 plus 1/2 is 3/2? Is that true? Don't make me think. Yeah, good. And so, the electric potential inside minus KQ over 2R cubed R squared plus 3KQ over 2R, which is often written as KQ over 2R, 1 minus let me make sure I haven't made any algebraic errors. Nope. We'll talk about how the normal components of the electric field, that discontinuity as an example, but this is important. It is the continuity of the potential that creates this term. And look at dimensional consistency. This is just a number. So this better be just a number without a unit. So this is meter squared over meter squared. It cancels. It's a number. Yeah?
I was getting the outside one correct, and then the inside one, I was like, there's this extra term going from I don't know where, so I waited.
And so you have it. So one of the things I will do, I will assign is problem. It's a worked out example. It's almost a worked out example. Turn to page 86, example 2.8. Example 2.8 is just a spherical shell.
Should the 1 be a 3?
Ah. Oh, yeah, thank you.
Because R equals
Yep,
capital R.
this, good catch.
That R equals capital R, it should be 0, right? That R equals
Right,
capital
right,
R gives
yeah.
it 2 in there, 2 cancels the 2, and you get the outside.
R equals capital R, it should be KQ over R.
Yeah, because
Right.
that gives 3 minus 1.
One,
is
right,
2, and
2.
then 2 cancels the 2.
Yep, perfect. Lesson number 1, always good to have a string theorist in your class. You guys missed it. How many other mistakes did I make today? But go through the notes and let me know. Any questions?